Good morning, chemistry. I hope all of you are doing well. You got through your first week of distance learning through Port Huron High School. I'm pretty much going to run every week just like that. I'm not going to overload you guys. I'm not going to give you a ton of stuff. I'm going to try to teach you kind of one important idea or concept or method each week. Last week's big goal was for you to understand the basics of the different kinds of bonds. So at this time, you should be able to tell me what an ionic bond is, what a covalent bond is, and then with a covalent bond, tell me the difference between a polar and a nonpolar bond. And that was the goal for last week. Each week I'll do a video that'll teach, and then a small assignment that'll just make sure you understood what was in the video. Sometimes it'll take the place of an activity like you had last week. Sometimes, like this week, it'll just be doing practice problems. Some weeks it'll be a lab. Like next week, your only assignment is going to be a live online lab where I kind of have the lab done in front of you and you take data of somebody else doing the lab on the video. Either way, a lot of you have done a really nice job of emailing me questions, texting me. Please feel free at any time to call. I'm sorry, please don't call, but text or email any kind of questions. For the most part, I can almost always answer them immediately. So if you're sitting there and you're really struggling, don't struggle. Just text me the question and I can get right back to you. That way you can move on. Okay? All right, so what I want to start off with first is a quick review of where you should be right now. First, you guys talked about ionic bonds. Now the thing of it is that when we talk about bonding, what's happening is that elements by themselves are relatively unstable. There are some elements that are very stable by themselves, there are some elements that aren't. Either way, all elements are always seeking out a way to become more stable than what they are right now. And as we talked about before, all elements want to have 8 valence electrons. So if something doesn't have 8 valence electrons, it's going to seek out another element to help it get that 8. For example, the most common ionic compound that you guys are aware of is sodium chloride, NaCl. Now, if you look at these two compounds, if you look at these two elements, you have Na, which, if you look at your periodic table, is in group 1. Okay? It's 3s1, which means it has 1 valence electron. Now, if we mapped out its electron configuration, like we learned before, it'd be 1s2, 2s2, 2p6, 3s1. So if we did the orbital notation, you would have something that looks like that. Now, if you look at that, you'll notice that it's how many electrons away from being completely stable? And the answer is 1, right? It has 1 electron that it needs right there. So it's going to seek out another element to take that electron from, and that other element is going to be chlorine. Chlorine, if you look at your periodic table, is in group 7, so it's going to have 7 valence electrons, meaning that all it has to do is to gain 1 to be happy. So electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p5. And just like with sodium, if we drew the orbital notation, it would look like that. So what's going to happen here is you have a situation where this, when you look at the orbital diagram, like I talked about before, it looks as if all it has to do is gain 1 to be happy. Whereas in reality, there's, as you can see, a 3p out here and a 3d. So if it gained 1, its valence shell would not be full. There would just be 2 in the outermost level instead of 8. On the other hand, if you look at chlorine, chlorine has 2 and it has 5. So in its outermost energy level, it has 7 valence electrons, which means all it has to do is to gain 1. So what happens is this electron right here leaves sodium and goes to chlorine. So now we have a situation where the sodium lost 1 electron and the chlorine gained 1 electron. And it's a perfect partnership because now they formed a compound. And that's another thing for us to make sure we understand is that ionic compounds are called compounds. They're not called molecules. Now, the biggest characteristic then of an ionic bond that we have to know is that the electron is transferred. I'm pretty sure I spelled that wrong. That's okay. Okay. Now, to make this easy, in the activity we did last week, we talked a lot about using electronegativities. We're not really going to look a lot at electronegativities this week or next week, but instead, all you have to do is look at what 2 things are being bonded together. Okay? What we're going to look at is the fact that whenever we have an ionic bond, it's going to be ionic because you have something that wants to give electrons and something that wants to take electrons. Metals want to give, nonmetals want to take. So ionic bonds, for us, is always going to be a metal with a nonmetal. And if you forgot, if you look at our periodic table, we have our staircase that should be on your periodic table, and everything to the left of the staircase are nonmetals. I'm sorry, are metals, and everything to the right are nonmetals. Okay, so most of the periodic table are metals. Most of the periodic table want to give up electrons and form positive ions, and a small part of the periodic table will form the molecules that we'll talk about next. Okay, just to finish up ionic bonds, a couple of things we need to have in our head. First, characteristics. Number 1, ionic compounds are brittle. Brittle means that they break fairly easily and they break into a lot of pieces. Think about salt. Think about things that are crystallite in structure. Soap is not brittle. Okay, soaps are not ionic at all. So when you think of ionic bonds, just think brittle. Think of salt. Number 2, as you learned at the end of last week's activity, ionic compounds conduct electricity, but only when dissolved in water. Okay? And remember, why is this? Because ionic compounds split when they dissolve into ions. For example, salt, as we talked about before. Will split into 2 different ions when it's dissolved in water. And that will allow for electricity to be conducted through the water. Okay? One last characteristic. Hi, puppy. They have a very high melting point and a very high boiling point. Okay, it takes a lot of work to melt salt. You can, but it takes a massive amount of work. Also, when you have an ionic compound, it takes a lot of work to get it to boil. And it all boils down to the same reason. When you have an ionic compound, what you have essentially are ions that are together, like in a cube-like structure. And they're together because positives stick to negatives. It's called an electrostatic attraction. Positives stick to negatives. And it's really hard to pull these apart because a positive ion and a negative ion are really positive and negative. So it's really hard to pull them apart. So it's hard to boil it and it's hard to melt it. Now, today we're going to talk about Lewis dots for covalent molecules. Lewis dots for ionic compounds are done differently. And a lot of you were taught incorrectly, unfortunately, in past classes. So I want to make sure we know how to do this right. Okay? If I'm drawing the Lewis dot for sodium chloride, the first thing we have to do is draw the Lewis dot for the individual molecule. Now, if you remember, the Lewis dot structures for individual atoms show the number of valence electrons. Sodium has one valence electron, so we put 1 dot. Chlorine has 7. So how you do it is you do 1, 2, 3, 4. Okay, you put 1 on each side, and then you pair them up. 5, 6, 7. Okay? Now, as we just talked about, sodium is going to take this electron and give it to chlorine. So that electron from sodium is going to be right there. So what's going to happen is you're going to have a Lewis dot structure that looks like this. Sodium is a plus because it lost its electron. Chlorine has its own 7 plus the one from sodium. Now, since this gained an electron, we're going to put a bracket around it and put a minus. And that's how you do a Lewis dot of an ionic compound. It's done differently for one specific reason. If you look at this diagram, does it show electrons sharing in any way whatsoever? And the answer is no. It shows an electron being transferred, which is exactly what it should show. Okay? Now, for this next part, if you want to pause the video, please make sure that you have in front of you a periodic table. You absolutely have to have a periodic table to do the next part, because what we're going to do is we're going to talk about covalent molecules. Okay? So, this is the main thing today. Covalent molecules. Now, if you notice, I'm writing the word covalent, and next to it, molecules, not covalent compounds. Remember, the word compounds goes with ionic bonds, molecules goes with covalent. We don't say a water compound, we instead say water molecule. We don't say a molecule of salt, we say salt compound. Okay, you put the right word with the right bond, and that's important from here on out to do so. Now, covalent molecules are very different from ionic in one way. We are now sharing electrons. Now, why would we share electrons instead of transfer? Well, the answer is pretty simple. When we have something that wants to give electrons paired with something that wants to take electrons, then it's natural that the electron is transferred from one that wants to give to one that wants to take. But what if two nonmetals want to bond? Two nonmetals. Well, now we have a situation where we have two elements that both want to take electrons. Since you have two atoms that both want to take, then it's a tug-of-war situation that you talked about last week. Instead of them transferring electrons, now what they have to do is simply share. And by sharing, it's exactly that. They're sharing the electrons. Now, it's kind of an abstract thing to kind of think about, so let's talk about what that actually means, the sharing. If you look at something like carbon dioxide, okay? Carbon dioxide is two nonmetals. Carbon is a nonmetal, oxygen is a nonmetal. Carbon has 4 valence electrons, so it needs 8, like everything else. So it needs a way to get 4 more electrons. Oxygen has 6 valence electrons. Those atoms, both of them, need to figure out a way to get 2 more. So both carbon and oxygen both want to take electrons. Since they both want to take, they bond together and they share. Now, if you look at carbon, carbon has 4 valence electrons. So if we were to draw the Lewis dot, you would draw 4 dots around it. Just for sake of this part of the lecture, I'm going to draw it like that. Now, since we have 2 oxygens, I'm going to put an oxygen here and an oxygen here. This oxygen has 6. This oxygen has 6. Okay? So what's going to happen is these 2 electrons are going to move over here, and these are going to move over here, and what we're going to have is a situation that looks like this. Now you're going to learn how to do this in just a minute. But what I want to point out is that what we have here is a situation where this oxygen now, if you count them, has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And then when you look at the carbon in the middle, this carbon also has 1, 2, 3, 4, 5, 6, 7, 8. So by sharing electrons, all 3 of the atoms can now have 8 electrons. And what this ends up looking like is 2 bonds, because a bond is 2 electrons. One from one atom, one from the other. These electrons are still there because they're not involved in a bond. Then you have the 2 bonds over here. There's a bond, and there's a bond. So that's what carbon dioxide would look like. That's what a Lewis dot structure of carbon dioxide would look like. Now, again, if you counted oxygen, you got 1, 2, 3, 4, 5, 6, 7, 8. Because remember, a line equals 2 electrons. So if you have a single bond, that's 2 electrons. This is called a double bond because there's 2 of them. So that's 4 electrons. And that's a double bond as well. Now, covalent molecules have 3 distinct characteristics. One, they are soft. As we talked about, ionic compounds are brittle. Covalent molecules are soft. When you think of covalent molecules, I want you to think about soaps and oils. Number 2, they are bad conductors. Again, for the exact same reason we talked about with ionic bonds. Ionic compounds are good conductors because they split when they hit water. Covalent molecules are terrible conductors because they don't split when they hit water. And number 3, again, for the same reason, these have low melting points and low boiling points because there is no electrostatic attraction. Now, what we're going to do, which is most important, is we have to learn how to do 2 things. We have to learn how to do a Lewis dot structure for a molecule and how to predict its shape. what I would like you to do is have two things in front of you. First is the periodic table, and second is this chart that is in your notes. Now, if you're able to print, that's fantastic. Print everything out. If not, that's totally okay as well. You can just have this on your computer screen. Okay, and just refer back to it. The first thing we need to learn is how to do a Lewis dot structure for a covalent molecule. Now, Lewis dot structures for covalent molecules are a little bit more difficult because we're sharing electrons, and they have a lot of different ways that can happen. Now, if you look at your notes that's attached to today's Google Classroom, everything I'm about to say is given to you in a step-by-step manner. Okay? The first example we're going to start off with is water, a molecule that we're all very, very aware of. Step 1, count the total number of valence electrons. Okay? So if you look at H2O, hydrogen has one valence electron. It's in group 1. It has one valence electron. And we have two of them. So we have two. Oxygen we have 6 valence electrons because it's in group 6. And we only have one of them. So it's 6. So just to be clear, this is valence electrons. And this is how many atoms? We add those up, and we have 8. So that's step 1. Step 2, choose a central atom. Now, most of the time, this is common sense. You look at the molecule, and whatever you have a one of, that's usually your central atom. Okay? It's pretty much as simple as that. Usually, whatever you have one of, that's your central atom. If you have one of two different things, then chances are you have something that's in a line, so it doesn't really matter what's the central atom. And we'll talk about that in a minute. But if we look at water, the central atom is obviously going to be oxygen because we have one oxygen, okay, and we have two hydrogens. So we draw oxygen in the middle, okay? 3, draw all the others around it. So we have the central atom, which is oxygen. Now we're going to draw around it H and H. Now you'll notice I used a line to connect the H to the O. Each electron, if you remember, is 2 electrons. I'm sorry, each line is 2 electrons. So just by connecting the H's to the O, I just used 4 electrons. 2 electrons here and 2 electrons here. So what I'm going to do is I'm going to go back up to this total right up here, and I'm going to take 4 electrons away from that because I used 4 of them. And now I have 4 left. Step 4 is to satisfy octet of outside atoms. Now, remember that all atoms want to have 8 valence electrons, but there are 2 exceptions to that, hydrogen and helium. As we learned way back in October, hydrogen and helium only have 1 energy level, so they can only fit 2 electrons. So hydrogen does not need 8, hydrogen needs 2, and that's it. So if you look right now, both of these hydrogens have 2, so you can't add any more. So you leave it. Step 5. add any electrons left to the central atom. Okay? We have 4 left. 1, 2, 3, 4. Now, a quick question that should pop in your head right away. Why didn't I do that? Okay, this is bad. No molecule on the planet Earth looks like that. Okay? And the reason is real simple. These are bonds. Both of these lines represent 2 electrons. That's also 2 electrons, and that's also 2 electrons. But the difference is that these are electrons involved in a bond. These are electrons that aren't. And they always go next to each other. Okay? Electrons that are non-bonding will always prefer to be next to each other rather than next to a bond. Okay? We used 4 electrons, so we go back up here, and we've used all of our valence electrons. If we have any electrons left, which would be highly, highly unusual, you go through a whole other procedure, which we will not do. Okay? So what we're going to do is we have to do 2 things now. Now that we know what the Lewis dot of water looks like. Okay, now the Lewis dot then of water looks like this. The first thing I want to do is ask you what kind of bonds are in between the H and the O. Now, since the H and the O are 2 different elements, both nonmetals, right away is covalent. Okay, but you can't just say covalent. There's 2 different kinds of covalent. There's polar and there's nonpolar. Now, here's the good news. The only bonds that are going to be nonpolar are going to be diatomic. Okay, Brinkelhoff. Now, as you'll learn in AP Chemistry, if you take it next year, there's obviously exceptions to this. But for our purposes, the only non-polar covalent bonds you're going to see are when an atom is bonded to itself. Anytime a nonmetal is bonded to a different nonmetal, it's going to be polar. So if you look at water, that right there is a polar bond, and that right there is a polar bond. Now the last thing we got to do is figure out its shape. What shape is it? Now unfortunately we're not in class, so we can't look at things in a 3-dimensional way, but what we're going to use is something called VSEPR. Valence shell electron pair repulsion theory. Now do you need to memorize that? Of course not. All you got to do is just think about this. Electrons are negatively charged particles. So if you try to put 2 electrons next to each other, they're going to repel each other. They're going to push away. The only way we can take 2 electrons and pair them, as we talked about back in December, is when they spin in opposite directions. If you remember, that was the Pauli exclusion principle. They had to spin in opposite directions. Now, when they spin in opposite directions, we can put 2 electrons together, but that's it, because there's only 2 different directions you can spin. So if I try to take another pair of electrons and put them next to another pair, they're going to push away from each other. But the issue is that as much as they want to push away from each other, they're still attached to a central atom. So if you can imagine 3 people or 3 balloons that are all trying to get away from each other, but all tied to a rock that's suspended in midair. They're going to get away from each other in 3 dimensions. And what that does is that makes different molecules have different shapes, which is VSEPR. That's the repulsion part. Okay? Now, what you do is you just go to this chart right here. You don't have to memorize these. Okay? This is a chart that we'll work a lot with, and it's a chart that we'll work a lot with in AP Chemistry. Now, the thing is all you do is you match what your Lewis dot looks like with something on this chart. Okay, does your Lewis dot look like this? And the answer is definitely no. Does it look like that? No. So if you look through all of these, you'll see that water looks exactly like this drawing right here. So the shape of water is bent. And it's that simple. It's bent because what's happening is these electrons right here are pushing it down. It's pushing that down like that. So the shape of this is bent. Now in AP Biology, you're going to talk about this quite a bit because the shape of water gives it many, many very particular characteristics that allow it to be one of the most important molecules in life. Okay? All right, so let's practice. What I'm going to do is I'm going to do a bunch of practice, and then your homework is going to be to keep practicing. What I'm going to do for each molecule is I'm going to draw the Lewis dot, and then we're going to predict the shape. Draw the Lewis dot, predict the shape. So, the first one we did was water. Let's do PCl3. Phosphorus trichloride. Phosphorus trichloride. So if you look on your periodic table, phosphorus has 5 valence electrons. Chlorine has 7, and you have 3 of them. So step number 1 is to count your total number of valence electrons. So 7 times 3 is 21, plus 5 is 26. So we have 26 electrons to work with. Our central atom is going to be phosphorus because it's the one thing by itself. Next step is to draw the atoms around it. Cl, Cl, Cl. Now, a common question I always get is, does it matter where you put them? And the answer is absolutely not. Put them wherever you want. Okay? Because in the end, you'll find out it doesn't really matter. What does matter is that you use the proper number of electrons. So how many electrons did I just use? 1, 2, 3, 4, 5, 6. So I'm going to keep my tally over here. Minus 6. Now I have 20 left. My next step is to satisfy the octet of all of the outside atoms. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So now each chlorine now has 8. Now how many electrons did I just use? 6, 12, 18. I have 2 left. Phosphorus right now only has 2, 4, 6. So I give phosphorus 2 more. And I'm good. There's your Lewis dot. So now I look at my chart, and what exactly looks like that? And there it is. You got the central atom with 2 electrons that are not involved in a bond, and 3 bonds. That shape is pyramidal. So this is pyramidal. Next one. Let's try CS2, carbon disulfide. Carbon disulfide has 4, and then sulfur has how many? It's in group sulfur is in group 6, so it has 6. You have 2 sulfurs, so 6 times 2 is 12, plus 4 is 16. So we have a total of 16 valence electrons to work with. Our central atom is going to be carbon, because it's the one thing by itself. You put the 2 sulfurs around it. So I just use 1, 2, 3, 4 electrons. I have 12 left. The next step is to satisfy the octet of the outside electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, this sulfur is happy, this sulfur is happy. They both have 8. But we just used 12 electrons. So I have none left. Now, if you look at the central atom has only 4 electrons, and it needs to have 8. So, how do we get 8 around the central atom when we don't have any electrons to give it? And what we do is we take these electrons and move them down. Take these electrons and move them down. So what you end up with is a double bond. And that is how double bonds are formed. When you don't have any more valence electrons to satisfy the octet of the central atom, you let the outside atoms form another bond. Now you'll notice I formed a double bond on each side rather than a triple bond on one and double bond on another, because atoms want to keep things as balanced as possible. So this would be your Lewis dot structure for CS2. And if we look at our chart to try to figure out the shape, it sticks out to you right away that it's in a line, so it's going to be linear. So the shape of this is going to be linear. Next one I want to do, SBr2, sulfur difluoride. Sulfur difluoride. Now the thing with sulfur difluoride is sulfur dibromide is we have to make sure that we are using the rules we talked about with water. Okay, and that is this. When you have electrons that are in a bond versus electrons that are not in a bond, and this is what I'm talking about. So first, let's make sure we count valence electrons. So sulfur has 6, bromine has 7, and you have 2 of them. So 7 times 2 is 14, plus 6 is 20. So we're working with 20 valence electrons. A central atom is going to be sulfur, because it's the one thing by itself. We put the bromine here and the bromine here. Okay? That used 4 electrons. So now we have 16 left. Okay? The next step is to satisfy the octet of the outside atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I just used 12 electrons. That leaves me with 4, which is good because unlike the previous problem, the central atom has 4 and needs 4. So there's 1, 2, 3, 4, and that uses the 4. So now we're done. But look at that. And remember what I talked about with water. Does it exist like that? And the answer right away should pop in your head that it is no. Nothing looks like this. Okay? Why? Because electrons that are not in a bond versus electrons that are in a bond prefer to be next to each other. So what will happen is that these should be next to each other, not apart. So this looks just like water. They'll be there, and the bromines are here. And if you remember, you go back to your chart to figure out the shape, and some of you probably already know it. When you got the 2 electrons on top, and it's bent, it is called bent. Okay? So hopefully some of you are starting to get the hang of it. But that's exactly what you do. You do the exact same method every single time, and you use your Lewis dot to get to the name of the shape. You cannot figure out the shape without the Lewis dot drawing. You cannot. Now, next one I want to do, which one was that? SBr2. Let's do this one. SiF2Br2. Now I know this looks scary, but it isn't. Okay? Always the same thing. Silicon, 4. Fluorine has 7. Bromine has 7. You have 2 bromines, 2 fluorines. So you have 14 plus 14, which is 28, plus 4, which is 32. So we're working with 32 electrons. Our central atom is going to be silicon because it is the only atom by itself. So we have Si. Then you draw the outer atoms around it. F, Br, Br. Again, common question, does it matter where the F's and the Brs are? The answer is no. You can draw FBr, doesn't matter. Next step, I used 2, 4, 6, 8. 32 minus 8 is 24. Next step is to satisfy the octet of the outside atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6, 12, 18, 24. I just used all the electrons that I have left, which is good because I don't need any more. Okay, silicon in the middle has 2, 4, 6, 8. So it's happy. And we are done. So now we look at our chart. And what does this look like? You have a central atom with 4 things sticking out of it with no electrons by itself. That is tetrahedral. So the shape of this would be tetrahedral. All right. Next one I want to do, and what I'm trying to do is I'm just trying to do different kind of things that you'll run into. The next one is COI2. COI2. First up, count your valence. Carbon has 4, oxygen has 6, iodine has 7. So 4, 6, 7, and you have 2 iodines. So 7 times 2 is 14, plus 6 is 20, plus 4 is 24. So we're working with 24 total electrons. Now my central atom usually is the one thing that's by itself. So as you notice, we have carbon and oxygen by itself. So which one is it? Well, if that's the case, have a look. And if you have carbon, carbon is always a central atom. Carbon is never not a central atom. I will not be giving you an example like this where carbon is not the central atom. So carbon's our central atom. So you put the other ones around it. You have I, you have another I, and you have an O. Again, if you didn't draw it like that, that's okay. Doesn't matter. You just used 2, 4, 6 electrons. So now you have 18 left. Next step, satisfy the octet of the outside electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that unfortunately uses all of our electrons. We don't have any left. And if you notice, our carbon has only 6 valence electrons around it. Now, this is easily solved, as we talked about before. You just got to form a double bond. Question is what do you form the double bond with? Do you form it with the oxygen or the iodine? And here's your simple answer. If you look at the periodic table, okay, oxygen right here has 6 valence electrons, meaning it's got room for 2. Iodine has 7 valence electrons, meaning it's got room for 1. So if you look between iodine and oxygen, oxygen is far more apt to form a double bond. Now you'll notice when I form the double bond, I scratched out those 2 electrons, and that's important that you do that, because then if you don't do that, then the oxygen is going to be left with 10 valence instead of 8. So what this ends up looking like is this. Okay, Last step, its shape. So we look in our VSEPR, and you look, and you're going to end up all the way on the bottom there. Okay? I drew it sideways. Okay? So it looks like that, but that's a trigonal planar. And what that means is that it's trigonal, which is exactly what it sounds like. It's going in three different directions. But the word planar means that it's all in the same plane, which means it's all on X, on Y, or on Z. Okay? Which is important. What that means is that if you're looking at it in XYZ type format, it means that it's not as if the I's are on the X and the O is on the Y. Okay, it's not, the molecule is all in one plane, flat like a piece of paper. Okay? Doing great. This video went way longer than I thought. All right. I want to do two more, and then we are done. No, I want to do three more. Sorry. First one is BCl3. I want to do boron trichloride because boron is an exception to the octet rule, and it's something that we have to know at this level. Boron, and I want you to write this, is happy with 6, not 8, for reasons we'll learn in AP Bio. But it has to do with its hybridization. Now, boron trichloride, you do the exact same thing. Boron, if you look on your periodic table, has 3 valence electrons. Chlorine has 7. 7 times 3 is 21, plus 3 is 24. Boron is our central atom. We draw the chlorines around it. We just used 6, so we're left with 18. We satisfy the octet of everything around it, and that uses everything. Okay? Now, normally what you would do right now is you would say, okay, boron right now only has 6 around it, so we need to form a double bond, and you would try to wrestle with which chlorine to use, and we'll talk about that a little bit later. But the fact of the matter is that you have to remember boron is one of the few atoms that is happy just like this. So you would stop right here, and you would not go any further. And the shape of this would, again, still be trigonal planar. Okay, you look at your chart, and it matches that second one right there, trigonal planar. So the shape of this would be trigonal planar. Okay? All right, 2 more. I'm going to use yellow paper now. Sorry about that. I ran out of white paper. Hey, puppy. All right, first I want to do O2. I want to show you what a diatomic molecule looks like. Okay? Now, oxygen obviously is a nonpolar bond. This is one of the only nonpolar bonds in your chart. Okay, oxygen has 6 valence electrons, so we have 12 total to work with. Now, the first step is usually to find a central atom. Well, there is no central atom, right? It's an oxygen bonded to another oxygen. So that's what you would start off with, is just put them together. You just use 2 electrons. You have 10 left. Okay? Now, the next step would be to satisfy the octet. So just pick one. Okay? So I'm going to pick this one. 1, 2, 3, 4, 5, 6. I just used 6. I have 4 left. 1, 2, 3, 4. Now, unfortunately, when you look at this oxygen has 8, but this oxygen only has 1, 2, 3, 4, 5, 6. So what has to happen is we have to form a double bond. So these electrons will come down, and you have that. So now you have this oxygen with 8 and this oxygen with 8. Nonpolar molecules, you don't even have to look at the chart, will always, always, always be linear because they're in a line. Now to that end, if you look at N2 has, this has 5 valence electrons, so we have 10 total to work with. Same exact process. Draw N next to itself, You just use 2, so now you have 8 left. If I satisfy this octet, I just use 6. Now I only have 2 left. So now I have those 2 right there. So you take this, put it there, form another bond, get rid of that. But still, 1, 2, 3, 4, 5, 6, you got to put that down. And what you end up with is that, a triple bond. And again, it's linear. This nitrogen has 8, this nitrogen has 8. You'll talk a lot about this in AP Biology as well, because this triple bond makes it so that our bodies can't break it. So even though we're breathing nitrogen a lot, most of the air you're breathing is nitrogen, even though we need it, even though it's one of the most important elements needed for amino acids to make proteins, we can't break that bond. We can't break it. In AP Bio, you'll learn about something called nitrogen-fixing bacteria, and you'll learn about the process of breaking that bond. The last thing I want to teach you is how to do a Lewis dot with a polyatomic. If you remember, a polyatomic ion is an actual molecule that has a charge. Okay, so this is phosphate. The idea of it being a polyatomic changes nothing. The only thing it changes for you is your method of counting the valence electrons. The first step would be to count the valence electrons, right? Okay, now phosphorus is going to have 5, and oxygen is going to have 6 times 4, which is 24, plus 5, which is 29. Okay, so you have 29 electrons. Now right away, the fact that that's an odd number should be alarming to you, because all of these things happen in pairs. So you can never have an odd number. But this right here, if you remember, means that this molecule as a whole has gained 3 electrons. So we have to add 3 to this. And 29 plus 3 is 32. Okay? If it had a 3 plus, that would mean that it lost 3 electrons, and therefore you would subtract 3 from that total. Now, once you've done that, everything else is done the same. Phosphorus is your central atom because it's by itself. You have an O, you have an O, you have an O, and an O. You just used 8 electrons, now you have 24 left. You satisfy the octet of all the outside atoms. And that uses all 24, which is okay because our central atom has 8 around it. So there you go. Now, this is going to be tetrahedral if you look at your chart. So you write down the shape. Now the only thing we have to do here is we do have to make some kind of notation to tell the reader that this is a polyatomic ion. So whenever you have a polyatomic ion, you draw a bracket around it and you put its charge on the outside. That way the reader knows that there's an extra 3 electrons in there. Okay? Now, your homework after watching this video is to go to the attachment that's on Google Classroom right now. Now, I've attached several things. I've attached a new periodic table in case you lost yours, or the 7 that I've given you. I've attached this video that you should watch first, obviously. And then I've attached the notes and the homework. Now, the notes and homework have a chart at the end that looks like this. Okay? Now, I have just done the first 10 of these for you. And what you're going to do for each one of these is you're going to just do the first 3 columns. I want you to draw the Lewis dot using the method you just learned. Using the chart, you tell me what the shape is. Now, this column is the polarity of the bonds. Now, as I said, every single one of these should be polar unless it's diatomic. Okay? Unless it's diatomic. And that's your homework for this week. Your homework for this week is to finish these 3 columns for this chart. Due on Sunday, midnight. And as always, if you have any kind of question, please let me know. Now, before I stop, just so you guys know, I fully realize that you can't draw on a Google Doc, okay? However, I do also know that you can't get this shape without that drawing. So when you submit your Google Doc, just put this in there, okay? I'm assuming that you're going to do these drawings on a separate sheet of paper. So your Google Doc, when you submit it to me on Sunday, is only going to have these two columns. Okay? All right. Hope you guys all have a great week. I really miss you guys. Please stay healthy. Please stay safe. And please be smart. Talk to you soon.